last video, Katie used R to show us our car dataset. Now we need to learn how to model this car dataset using multiple linear regression. This can often be a confusing topic, but thank God for Griselda. She's going to teach us all about the theory.
That's right, Brittany. I will teach you about the theory behind multiple linear regression with interaction. It can seem a bit complicated, but don't worry. We will start with a very basic model, also known as a simple linear regression model, and build from there. As can be seen in this pyramid, simple linear regression is the foundation of regression analysis. From it, we can advance onto multiple linear regression until we reach the peak, at which point we can include interaction terms. A simple linear regression model uses one independent variable x to predict the response or dependent variable y. Suppose we want to determine the horsepower of a set of vehicles, and the only information we have available are the miles per gallon, or mpg, for each car. Using simple linear regression, we can set up horsepower as a linear function of mpg. Our goal is to find good estimates for the betas, which are the unknowns. x1, on the other hand, represents our known values for mpg, which can be obtained from the dataset. I want to take a moment to clarify the difference between categorical and continuous variables. Categorical variables are variables that have a finite number of categories or distinct groups. Examples include gender and smoking status. It is helpful to think of them as variables that describe qualities or characteristics. For our model, cylinders is a categorical variable. Cars may have the quality of having either 4 or 8 cylinders. Continuous variables, on the other hand, are numeric. Examples include age, weight, and height. In our model, the continuous variable is miles per gallon. It is important to note that the response variable for linear regression must be a continuous variable. Let's compare simple and multiple linear regression. Notice that the only difference is that multiple linear regression uses 2 or more predictor variables, whereas simple linear regression only uses 1. Instead of just using mpg, we are now using a vehicle's mpg and number of cylinders to predict its horsepower. We are now ready to discuss interaction terms. Note that this is the same multiple regression model from the previous slide, but with an extra independent variable called model year, and a super important difference. We added an interaction term. An interaction effect occurs when the effect of one variable depends on the value of another variable. It indicates that there is a second predictor that affects the relationship between a particular predictor and the response. In this particular model, we want to see whether the effect of mpg on horsepower varies depending on the number of cylinders. Stated more generally, we want to see whether the effect of x1 on y changes with x2. Now you might be asking yourself why we chose these particular variables. The reason is that we are interested in figuring out whether we can predict a vehicle's horsepower given mpg, cylinders, and model year. We chose mpg as a predictor because it is something that people usually look into when buying a car. The lower the mpg, the less miles you drive per gallon, meaning the more you spend on gas. The higher mpg, the more miles you are able to drive per gallon, meaning that you save on gas. Generally, the higher the horsepower, the lower the mpg, and so the higher your gas costs. We chose cylinders because it is a factor that also affects horsepower. The more cylinders a vehicle has, the more horsepower it has. The less cylinders, the less horsepower. Model year was also selected to see whether newer cars may have greater horsepower than older ones. This last term represents our interaction term. Interaction terms are used when you suspect that a variable has a completely different slope for different subgroups in the data. In our case, we suspect that the slope of mpg differs depending on whether a vehicle has 4 or 8 cylinders. Now it's time to check whether Model A is appropriate or needs improvement. By running the following R code, we get the following summary table. Going down the list, we can see the estimates for beta 0, the intercept, beta 1, beta 2, beta 3, and beta 4. We can see that the model year has a very large p-value, greater than 0.05, thus it is not significant. Note that sometimes you might want to include certain variables in a model even if they are not significant. However, in this case, we do not consider model year to be extremely important in determining horsepower as the other variables. Also, it doesn't have a wide range. Therefore, it is okay to drop this variable. Without model year as a variable, we are left with model B. We want to use MPG in cylinders to estimate horsepower, and we believe that the effect that MPG has on horsepower varies depending on the number of cylinders. In other words, the effect of MPG on horsepower for a car with 4 cylinders is different than the effect of MPG on horsepower for a car of 8 cylinders. As can be seen from the summary table, the model improved by dropping model year. MPG, cylinders, and the interaction term are all significant at the 0.001 or 0.1% level. The p-values are all under 0.001. We obtained the values of beta 0, beta 1, beta 2, and beta 3 respectively by going from the top to bottom of the estimate column. The interaction effect results in lines with different slopes, in lines that cross, not just in parallel lines or lines with same slopes that are higher or lower than the other. We can see this in the following plot from our data. In the summary table, we saw that the coefficient beta 3 for the interaction term is negative 1.1. This indicates that the slope of horsepower versus MPG is 1.1 points lower for cars with 4 cylinders than for cars with 8 cylinders. Now let's discuss how to interpret the betas. If we want to figure out the expected horsepower given 4 cylinders, we simply plug 4 into the x2s. Similarly, you would plug 8 into the x2s to find the expected horsepower given 8 cylinders. The values of dummy variables are arbitrary. You could also recode 4 and 8 such that cylinders 4 is equal to 1 if a car has 4 cylinders and 0 otherwise, and cylinders 8 is equal to 1 if a car has 8 cylinders and 0 otherwise. Beta 0 represents the intercept of the line for 4 cylinders. Beta 1 represents the slope of MPG for 4 cylinders. Beta 2 is the difference of the intercepts of 8 cylinders minus 4 cylinders, and beta 3 is the difference of the slopes between 8 cylinders and 4 cylinders. Now I will be showing a step-by-step calculation for this. In the next video, Yamini will explain the assumptions for multiple linear regression with interaction, and we will check whether our model meets those assumptions. See you soon.